Okay, as I was saying, we're doing these topics today. These are only 3 sections in our textbook, and they're not the whole chapter. I guess the whole chapter is 7 sections. So we're only covering the first 3, impulse momentum and impulse momentum theorem. Those are 2 sections, and conservation of momentum is the 3rd sections. There are some problems on collisions, but we're not discussing collision in detail. I gave you homework problems on it because it's basically conservation of momentum, but we're not discussing it in class in terms of differentiating between elastic versus inelastic collision and these kinds of stuff. But essentially, it's application on conservation of momentum. Okay. So let's get started right away because we only have so much time. So yesterday I gave a very brief introduction of momentum as an analogy with energy. So last time we said we had a model for energy. If we have a system consisting of objects, these objects have energies. Let's say first object has an energy, total energy E1, second object has total energy E2, and this object has energy E3. Then the total energy of the system is the sum of all energies. It was, of course, kinetic energy, potential energy, thermal energy, and stuff. But I'm using this notation just to have an analogy with momentum now. We also discussed that we can have energies transformed among themselves between particles in the system. And we can have energy transfer into the system or out of the system by doing work on the system. So this is energy transfer through work. And this was the basic energy model. We have essentially the same thing for momentum. If we have a system, we already know what a system is by now. This system has objects. These objects not only have energies, but also momenta, because every object has mass and every object has velocity. So all of these objects have momenta. If we have this object having momentum P1 and this object have momentum P2, momenta are vectors. So I'm putting the arrow over. These momenta can be transferred between the particles because the particles are interacting with each other. And we can also have momentum transfer into the system or out of the system, but this time through impulse. And we will see what that means. Okay. The basic relations were, first, the total momentum as well is denoted by capital P, and it's the sum of all momenta of individual particles, just as the energy was the sum of all energies of individual particles. We had a definition of work as force times displacement. And this was defining what this object is, what this quantity is. And then we had a cause and effect relationship, or what we call the work energy theorem, saying that the work done on a system causes the total energy to change. And finally, we had a definition of isolated system. If we have an isolated system, meaning that there is no net work done on the system, which is essentially that there is no net force acting on the system. So isolated system means the total or net force equal to 0. Then energy is conserved, meaning that the change in energy is 0. So this is conservation of energy. Exactly the same way we have a definition of impulse, we denoted by the symbol J as the force, or the average force rather, times the duration over which the force acts. And we have a similar cause and effect relationship stating that the impulse is the impulse causes change in momentum, or rather the total momentum, big P. This was a definition. And this is cause effect relationship, and it's also known as the impulse momentum theorem. As you can see, it's exactly analogous to the energy case. And again, if we have an isolated system, meaning the net force is equal to 0, that leads to delta P being 0, or conservation of momentum. Exactly the same as the total energy was conserved, meaning that the sum of all individual energies is the same, but energies inside the system can change. But if the addition of all energies are the same number, then we're fine. Same here, we have the individual momenta can change, but the sum of all momenta has to be the same number if the system is isolated. This was the big picture of what we're going to do. So we can call this actually doesn't have a name for some reason, but we can call it basic momentum model. Let me put quotation marks because I just called it like that. Now let's discuss the details of all of these bullet points. Okay. So we start with our first item, which is the impulse. So we have interactions happening all the time. When two objects in a system interact over a very brief amount of time or a small duration, we define that as a collision. So a collision is an interaction between two objects during a brief time interval. I wanted to clarify this definition because when we think about collision, we usually think about crashing cars or things hitting each other. But the general definition of collision is just interaction between anything, like any contact between two objects is considered a collision if it's happening over a small enough time. Okay. And collisions sometimes may seem instantaneous, like if you're kicking a soccer ball or if you're hitting a baseball, or if you're doing an interaction that your eye cannot, like you have limitation in the amount of time that your eye can see, right? But if you have a super fast camera that can capture all the intervals, and you had a video for a soccer ball being kicked, for example, you will see the ball being kicked. In the beginning, it was a round ball like that, and during the contact, it squishes a little bit, and then after it leaves again, it comes back to the original shape. Let's say this is the leg of the guy, just to give a sense of what's going on. So this is the initial point of time, and this is the final after the ball leaves his foot. And this is in between. So this is maximum compression. This is when the force acting on it is maximum. And all of this is contact time. So the guy has his leg in contact with the ball all the time. Okay, until they're separated. This defines the contact time. This is the delta T that we had in the definition up above here. And this is typically very small, like typical values for interaction time goes between 1 millisecond to 10 milliseconds. Okay, so this is 1 over 1,000 of a second. So that's very small. Your eye cannot detect that. That's why we think about it as instantaneous, but it's not really instantaneous. It has some time taking place over. So usually this force is very large. And when we have a large force acting over a very small interval of time, we call this an impulsive force. So an impulsive force is a large force acting over a brief amount of time. An example of that would be just the picture that I showed you before here, which is the soccer ball being kicked, or a tennis ball being hit by a racket, or any situation like that. Intuitively, we know that a harder kick or a longer time duration will have the ball leaving with higher speed, right? If the contact time is longer, the speed will be greater at the end. And if the kick is harder, the ball is also gonna leave with higher speed. So we quantify that by defining a quantity that combines both the intensity of the force and the duration. So we define the impulse and we denote it with the symbol J as the average force multiplying the duration of multiplying the contact time. And the reason why we use the average force and not the actual force is two things. First, The actual force is very complicated. Like in general, it's not constant. For example, in the beginning here, the force was starting slowly, and then in the maximum compression, it was very large, and at the end, the force decayed. So the shape of the force is not straightforward. So we take the average of that. And also, it's a very brief time. So the average force really captures the physics really well. We don't need to know about all the details. So we only care about the average force because it's like 1 millisecond. So that's good enough for applications. So this is our first important equation, the definition of impulse. I will use 3 bars instead of 2 because whenever I write this down, this means a definition. And we can take an example on that. So for example, if we have a ball bouncing from the floor, okay, let's draw it very close here. A ball bouncing from the floor, if we want to calculate the impulse the floor delivers to the ball, let's assume the average force of the floor on the ball is 150 newtons, and the contact time during which this happened was 1.2 seconds. Then the impulse is just 150 newtons multiplying 1.2 seconds, which gives us, oh wait, I wanted to have this as 8 milliseconds. As I said, it's very small, so it cannot be 1.2 seconds. I wrote down the answer rather than, so this is 0.008 seconds in SI units. And this is 1.2 newtons times seconds. This unit, Newton seconds, is equivalent to kilogram meter per second squared. And this is because 1 Newton is equal to 1 kilogram meter per second squared. So when you multiply it by a second, 1 second in the denominator goes away. This is the unit that we usually use. We don't use Newton seconds a lot. We usually use that because it's connected to momentum. If you look at this, this is unit of mass, and this is unit of speed. So it's connected to momentum. So we usually use kilogram meter per second and not Newton second, okay? This is the impulse. This is just the definition of impulse. Now we go to discuss momentum. So we know from experience that if we give a kick to a heavy object, that will leave it with a speed less than the speed we will get if we kick a light object, right? So we want to have we want to quantify this relationship between the kick or the impulse and mass of the object, describing if it's heavy or not, and the speed or velocity after the kick. So we want to connect all of these pieces together. So for this example, we will consider a puck moving with velocity v initial, and it has mass m. Okay, and then this puck is being hit by a hockey stick. Okay, so let's draw this. During the contact, there is a force, there is an average force from the hockey stick on the puck. So this is the situation before. This is the picture before. This is the picture during the kick. And now we have another picture after, with the puck moving with final velocity VF. And we want to connect all of these together. We want to connect VI, F average, VF. And also there is delta T here, because this act happens in an amount of time, delta T. So to connect these pieces together, we will use, again, kinematics along with Newton's second law. So we know if we want to calculate the final velocity and we have the initial velocity and time, we have this kinematic equation, V final equal V initial plus A average delta T. And this is the same equation as before. I just put the arrows because these are vectors. So there is nothing new here. And we can replace this A average from Newton's second law because we know F. We know A from Newton's second law is equal to force over mass, right? So if we substitute that, we get velocity final equal velocity initial plus F average multiplying time over mass. We can multiply both sides of the equation by the mass to get MV final equals MV initial plus F average delta T. Or we can rearrange that, putting F delta T on one side and MV is on the other side to get this very important relationship. This tells us if we act on the puck by an average force for an amount of time delta T, velocity changes from V initial to V final. This is what is known as the impulse momentum theorem, written down explicitly. There is another form, compact form. We will see it now. And it only is really if we already realize that as impulse, right? Impulse J. This is from the definition above. We will define momentum to be mass times velocity. I know we defined it last time, but now we're doing everything systematically. So this quantity that appeared in the derivation, we define it as momentum and we give it the symbol P, small p for individual momentum. Or actually, let's just call it big P if this is a system. And this is defined as mass times velocity. This is also a very important equation. It's a definition. And in terms of these definitions, defining this as J and defining this as P final and this is P initial, we get the impulse momentum theorem in this form. Nothing new here, just rewriting the quantities with their names, which is just J causes change in momentum. So the impulse causes change in momentum. This is the impulse momentum theorem. The formula above is the explicit formula, giving you the force, the time, and the mass and speed. And the second form is a little bit compact because it's just the impulse as one thing and momenta as the effect of that thing, okay? It's important to know that momentum is a vector quantity. So again, it has magnitude and direction. And if we're doing one-dimensional problems, then momentum is a signed quantity. So if it's going to the right, it will be positive. If it's going to the left, it will be negative. And most of calculational errors come from this, not taking into account the sign of momentum. When we do conservation of momentum and we say, okay, add all the momenta before and add all the momenta after, you should add them with their respective signs, not just add the numbers, okay? This is a common mistake, so I just wanted to point it out. This is the impulse momentum theorem. So let's take an example on how that is applied. So assume we have a ball coming to a wall with velocity 1.3 meters per second. This is a wall. Okay, and this ball has mass m equals 0.25 kilograms. This is before, and then this is the contact time when the ball was in contact with the wall, and then this is right after the ball leaves the wall, and we know that the final velocity is equal to negative 1.1 meter per second, because we're taking into account the direction as well. Okay, so this here is before, this is during, and this is after. And in this question, we want to calculate the change in momentum and the impulse from the wall on the ball, okay? So the change in momentum, we can get it from just calculating the initial momentum and calculating the final momentum, and then subtract final minus initial, okay? So initial momentum is mass times velocity initial. So it will have the same sign of the speed of the velocity. So if the velocity is positive, momentum will be positive. And if it's negative, then momentum will be negative as well. So this is 0.325 kilogram meter per second. And then we calculate the final momentum, which is mass times velocity final. I dropped the arrows because we're working one dimension, so it's not necessary, as long as we're taking care of the signs. This is 0.25 kilograms multiplying negative 1.1 meter per second, giving negative 0.275 kilogram meter per second. This is the initial momentum. This is the final momentum. So if we want to calculate the change in momentum, this is final minus initial. So this is negative 0.275 kilogram meter per second minus 0.325 kilogram meter per second. And if we calculated that, we get negative 0.6 kilogram meter per second. Okay. So we calculated the change in momentum. Now we want to calculate the impulse. And right away we go to the momentum, impulse momentum theorem, because it just says that the impulse is equal to the change in momentum. So we're already done. So the impulse is itself negative 0.6 kilogram meter per second. And you can see the connection between the units Newton seconds and kilogram meter per second from the impulse momentum theorem, because on one side we have the impulse, on the other side we have momentum. We know momentum has units of kilogram meter per second. And if impulse has Newton second, then the two units are the same. So this is a typical example on how you calculate the change in momentum and how you calculate the impulse. An application on that is how to slow down a fast-moving object during a crash. Like if you're in your car and something happened and you had to crash, the airbag blows up, right? So the point of the airbag here is to increase the contact time between your head and, like, instead of this happening in very brief amount of time, it increases the amount of time. So the impulsive force is small because we have the impulse equal to the impulsive force times time, right? And this is equal to delta P. From the impulse momentum theorem, J is equal to delta P. So this delta P is the same in both cases because you were coming from very fast speeds and then the final speed is 0. You stopped, okay? So this is the same in any case if you crashed with or without an airbag, because you came with the same initial speed and the final speed is 0. So this quantity is the same. So the force, the impulse force that you feel is delta P over delta T. So you can see it's proportional, it's inversely proportional to the time. So as you increase the time, you lessen the effect of the impulsive force. So that makes the crash gentler, okay? You can survive the crash. Otherwise, the impulse force will be very, very high and that can crash your skull. Okay, that's it for impulse momentum and impulse momentum theorem, really. We'll see a couple of examples in the activity. But let me actually give one more example to emphasize an important point before doing conservation of momentum. So another example. Here we have a rubber ball is thrown straight down onto a hard floor with velocity initial equal negative 11 meter per second, because I'm assuming up to be positive. Then it bounces. Let's have the floor very close here, because this is right before. This is right before the collision with the floor. This is right after the collision with the floor. Okay, let's number them as 1, 2, 3 instead of I, because we will have 3 velocities. And then the ball bounces and goes up until it stops, and when it reaches maximum height. So V3 is 0 at maximum height. So the point I want to make is that this problem must be solved into 2 parts. You cannot solve it at one time. You must realize that when you do impulse momentum theorem, it's right before and right after the collision. Right before and right after, because during that time, we're ignoring the effect of gravity. But after some time, when the ball bounces and goes up, gravity is working again. And I mean, gravity didn't stop in the first place, but its magnitude was very small compared to the impulsive force acting on the ball to bounce it back. So we ignored it in the first part, but we cannot continue to ignore it during the rest of the problem. So we must divide the problem into 2 parts. This is called the impulse approximation. Whenever you're doing right before and right after calculation with an impulse, you can ignore all other forces and just focus on the impulsive force because it's very big. But once you're done with that, you have to work with other forces again and restore the full problem. So this problem must be divided into 2 parts. So our target here is to get the maximum height, knowing that the average force the floor exerts on the ball is 400 newtons, and that the mass of the ball is 100 grams, or just 0.1 kilogram. And the contact time with the floor is 5 milliseconds. So it's 0.005 seconds. Okay. So we must divide it into 2 parts. This first part with collision itself is divided into 2 parts, before and after. And then there is, like, if you want to call it after number 2 or something, but we're calling it 1, 2, 3. For now, focus on before and after for the collision, because the strategy for solving a problem like that, we're dividing it into 2 parts, and we must get the velocity V2, because this is what connects the first part of the problem to the second part of the problem. This velocity, if we can get it, then we can use kinematics equations to get the maximum height the usual way. We did a lot of examples on that in the first part of the course. So if we can get V2, then we're good. To get V2, we need to use impulse momentum theorem. So again, let's calculate the initial momentum. P1 equal to mv1. This is 0.1 kilogram times the initial velocity, -11 meter per second. We calculate that this is just -1.1 kilogram meter per second. Momentum 2, mv2 equals 1.1 kilogram times v2, which we don't know. This is our unknown. Okay. Then delta P, which is change in momentum, is equal to 0.1 V2. I will drop the units for now, but you should know it's SI units. Minus 1.1. This is the change in momentum. This is the right-hand side of the impulse momentum theorem. This is the effect. Now to get the cause, it's the impulsive force multiplying the time. This is how definition works. And we have all the components we need. We have the force and we have the time, so we just multiply them. 400. I already converted everything to SI units, so I will write numbers. But before you do that, you must have your things in SI units. 400 times 0.05, this is just 2. Okay, this is 2. So I have J equals 2. And then impulse momentum theorem states that these two quantities are equal. So we have 2 equals 0.1 V2 minus 1.1. And you can easily solve for that. This is 3.1 equal 0.1 V2, giving V2 equals 31 meters per second. You see, we got a positive number because we consistently put our signs in the right way. So before we had negative because the ball was going down, and the math automatically turned out to be velocity going back up because it bounces. Okay. I think I just did a mistake here. I got the first momentum right, the second momentum right, but the change in momentum should be P2 minus P1, and this is already minus. So this should be minus 1.1, which gives us a plus. So this changes the result to 9 meters per second. The reason why I knew I made a mistake is that when I assessed the answer, and this is a good skill to know, when I get to assess the number that I got, I found it bigger than the initial velocity that I had. The initial velocity was 11 meters per second, and the final velocity was larger than that. But if you drop a ball, you know it goes no higher than the initial height that you dropped it from. So you expect it to be at least either equal or less speed. So when I got higher speed, I suspected something wrong with my calculations, and it turned out to be wrong. So this is a good skill to have. But this is a typical kind of calculation. Now we got the initial speed, which is here. I mean, initial for the second interval of the problem. Now we can use kinematics to get the maximum height from the equation. V final equal V initial plus 2a delta y. And V final is 0 because it's maximum height. So we know 0 equals 9 squared plus 2 times negative 9.8 meters per second squared for gravity, delta y. You can solve for delta y, you will find it to be 4 meters. So like it's very easy problem once you get V2. Any questions about impulse and momentum? Because I will move on to conservation of momentum now. Any questions before I move on? Okay. I guess this is number 3. Conservation of momentum. let's have the equations, the important equations above. Average times delta t. Just to have them in front of your eyes for some time. Okay, so this is what we have so far. So conservation of momentum happens when we have an isolated system, okay? But before that, let's consider just two objects interacting with each other. And in general, this interaction force will be very complicated between them. Like sometimes we don't even know how to calculate it. Let's assume we have two objects here. These, let me put them on a line to be easier. These two objects are coming towards one another. They come in contact and then they leave again. Okay. Let's call this 1 and this 2. 1 and 2. 1 and 2. Once these two objects are in contact, they are exerting forces on each other. So object 1 exerts a force on object 2, like let's call it F12. And object 2 exerts a force on object 1, F21. And from Newton's second law, these two forces are opposite in direction, equal in magnitude, and most importantly, acting on different objects, not on the same object. So the force from object 2 is acting on 1, and from 1 is acting on 2. This is during the collision, so this is during the amount of time delta t. So if we want to calculate the change in momentum for object 1, we know this is equal to the impulse on object 1, which in turn is the force acting on object 1. We call that F21, which is this force, times delta t. And the change in momentum for object 2 is G2 equals F12 delta t. And if we want to combine these two objects in one system and get the change in their total momentum, then we say the change in the total momentum of the system is the sum of the changes of the small momenta, which in this case will be F21 delta t plus F12 delta t. The collision is happening during the same time, so this delta t is the same. This is intuitive. We don't need to explain that. So we can take it as a common factor. What do you know about F21 and F12? one of them is negative the other, because we shouldn't forget we're dealing with vectors. So if I restored the vector notation, all of these are vectors. So they still have direction. I'm not writing just the magnitudes. These are directed quantities as well. Okay. So Newton's third law is crucial in conservation of momentum. It is the base of conservation of momentum. Without Newton's third law, there is no conservation of momentum. F21 is equal to negative F12. And that means this is 0. And this tells us that the change in the big momentum, the total momentum of the system, is 0. So as you can see here, the change in the momentum of the first particle is not 0, and the change in the second momentum is not 0 as well. But if you combine them together in one system, then momentum is conserved. Okay, and this is important because you need to choose which system is isolated. You need to see if the system is isolated or not. Because once we have the system as combining both objects, these forces F12 and F21 are now internal forces, not external forces. And we discussed earlier that only external forces can change momentum from the model above here. Only external forces can change momentum, but all these red arrows inside are internal forces. So if forces are internal, then Newton's third law ensures that all of them are equal and opposite in direction, and they cancel once we combine them in big system. So this is the basis of conservation of momentum. And we did that for 2 objects, but when we have a system of more than 2 objects, 1, 2, 3, 4, etc., you can do that pairwise. You can do that for these 2, you can do that for these 2, you can do that for these 2, and then you can do all combinations, and basically with the same argument, you conclude that for a closed system, the total momentum doesn't change. And the reason why is that there is no external force here once we choose our system. Okay? So there is no impulse. So the conclusion is basically that if F net, or let me actually call it F external, it's the same. I'm just emphasizing that it's the external force on the system. If it's equal to 0, then J itself, also external, is equal to 0, but because it's defined as this times delta T, then it's equal to 0 as well. And the momentum, the total momentum is conserved. Is this point clear? Okay. Again, conservation of momentum doesn't imply the individual momenta doesn't change, but rather it's saying that P1 initial plus P2 initial plus P3 initial plus ... however many particles you have is equal to P1 final plus P2 final plus P3 final plus ... And this is the basis of collision problems. If you have 2 particles colliding with one another, and this object was coming this way with some momentum P1 initial, and this was stationary, for example, P2 initial was 0. This is the situation before, and then assume, for example, that both objects stick together and move as one object with final velocity, then you will have the momentum of the first particle plus 0 equals the total momentum final. And this is basically saying the mass of object 1 times the initial velocity of object 1 equals to the total mass of both of them times the final velocity of both of them, because they're combined as one object now. So you can see all variations of collision problems as long as you know how to apply conservation of momentum. You need to understand how to choose a system to have no external forces acting on the system, and then momentum will be conserved this way. And you know what momentum is? It's mass times velocity. You know what impulse is? It's force times time. And impulse momentum theorem equates the two. Okay. I think that's it for momentum. Yeah, the rest of the chapter is elastic and inelastic collisions. I will not go over that. So we can take a 10-minute break, and after we come back, we will start working on activity 5, which has problems on momentum and conservation of momentum. Okay.